Hi, everyone. My name is Matt Dalkie. I'm the Senior Sustainability Manager for Lafarge Canada, for Western Canada. So my main responsibilities are primarily focused around carbon reduction across all of our product lines. So our product lines for Western Canada, if you're not aware, include aggregates, cement production, ready-mix concrete production, precast, and that precast is structural precast as well as pipe and box culverts and things like that, and asphalt. As well as some operations that look at construction as well. So that's my background is actually in cement manufacturing. I've worked in the cement industry for my entire career, studied in New Zealand and had a few years in the UK, then some in France, and now here in Canada for about 18 years now. If you're wondering what this photo is on my background here, this is our eggshell plant. Some of you may be familiar with this. It's visible from the highway as you go up to Banff, or between Banff and Calgary. So this is where the majority of your cement in the Manitoba region would actually be sourced from. So I'll just share my screen here. Okay, so you should see that now. So we'll just kick into it. I've got a few slides here, and then we'll start looking at some questions that people have. Okay, so first of all, I will pass off the slide deck. So, but I just wanted to touch a little bit on the words around carbon and some of the things that you may hear, and not only in this presentation, but in the industry in general. So embodied carbon is the carbon associated with materials and the manufacture of materials. Operational carbon, that's the carbon associated with operating buildings, or so that's your power, your HVAC, and things like that. Global warming potential, that is an LCA term, life cycle analysis term, used for describing the CO2. And then CO2 is actually can be split into CO2 and CO2e. So CO2 is just CO2, CO2e or CO2 equivalent are all of the other greenhouse gases that are calculated on a CO2 equivalent basis. The last two terms there, net zero, that has a few definitions, but can mean energy net zero, can be carbon net zero. But in this context, we're talking about carbon net zero over the life of the building. And then carbon footprint, again, lots of definitions here. It's usually all of the CO2 associated with the building and includes both operational and embodied and end-of-life carbon. So why are we talking about embodied carbon? So on the charts here, the darker green portions of the charts show embodied carbon. So as I said, the carbon associated with materials, and the light blue is the carbon associated with operations. So on the top chart, you can see that as the building is constructed, all of the carbon associated with the building is embodied. And then as time goes on, that you start adding up and adding in those operational pieces, and then you have a embodied carbon for the end of life as well. The bottom chart shows that as buildings become more efficient over time, the size of that circle is reduced. So the size of the circle represents the overall and total carbon. So as buildings become more efficient, the size of that circle is reduced. But when that reduction happens, the portion or the contribution of the embodied carbon becomes a much larger share. So that's why we're focused on embodied carbon. We'll talk about concrete sustainability. So concrete is the most used material on the planet after water. It does contribute to resilient communities because of its strength and durability. It's locally produced. It does contain recycled materials and is recyclable itself as well. Concrete buildings tend to have and require less finishes, and you use less energy, and the light color of concrete helps reduce the heat island effect when you're looking at concrete roofs, for example, or when you're looking at concrete pavement and parking lots. So when we look at concrete and carbon and where the carbon is actually coming from, so concrete, for those not intimately familiar with concrete, is basically comprised of essentially um, four different materials. There's aggregate, which makes up the bulk of the material, which is your gravel and sand. Your water, which makes up between 15 to 20% of the concrete volume. Cement is the next one, but in that cement is also included supplementary cementitious materials. And these are things that are like cement, but where they perform somewhat similar to cement, but they're not cement. And then we have air in there as well. And just with cakes and baking, admixtures can be used to impart specific properties for the concrete as well. So although the cement only accounts for 10 to 12% of the concrete, it actually accounts for around 80% or even higher than that of the embodied carbon, or the carbon associated with the concrete. So the main focus for the industry is primarily and initially, and has been for a number of years, a focus on lower carbon cement. So this is the cement manufacturing process. So we start off with all of these raw materials up here. So this is 1 kg of raw material. We grind those down into a fine powder. We heat those up in the kiln and preheater tower up to around 1400 or 1500 degrees Celsius, depending on the chemistry. And that's where all the most of the CO2 associated with cement manufacturing is released. So if you know a little bit about chemistry, limestone in the top left-hand corner there is a source of calcium, and this type of calcium is calcium carbonate, so CaCO3. When we heat that up, that CO2 is driven off from that calcium carbonate to create calcium oxide or lime. So that's the first step of the cement manufacturing process. So that's where the majority of the CO2 is released. About 60% of the CO2 associated with cement is released during as part of that process. And we're also using a lot of heat and fuel to actually heat everything up to those sort of temperatures as well. So we're releasing CO2 through the combustion of those fuels. We cool that down in step 3, rapidly cool it down, and we get clinker at that point. So starting off with 1 kilo of material in the top left-hand corner, we end up with 640 grams of clinker. So that weight difference is all of the CO2 that's been driven off. We mix that with gypsum and limestone, grind it up into a fine powder again, and at that point we get Portland cement or Portland limestone cement. So one of the things that the industry has been focused on and working on over a number of years now is what we call fuel switching. So using materials or fuels other than traditional fossil fuels to provide that energy to heat everything up. So traditionally, coal has been the fuel of choice for most kiln lines. So switching that out and moving over to other lower carbon or waste fuels. So it does only address the fuel emissions. Some fuels are assumed to be carbon neutral, and these are biogenic materials or biogenic fuels, as well as a biogenic portion of some of the other fuels, like tires, for example. They do have a certain level of biogenic content in there, so that's taken into account as well. In terms of how much fuel can be used, it is limited by the fuel type, like what the fuel source is and the process type, but we can reduce somewhere between 5 to 40% of our total emissions for cement production by switching to these other alternative fuels. And this has been in use and available worldwide for a number of years now. The other thing that we have done in Canada is actually switch from Portland cement, which is the traditional cement that has been used in Canada, and switching that over to Portland limestone cement, which started production around 2011 in Canada. So with Portland cement, we're able to add between 5 and 15% limestone, and with Portland limestone cement, we can add up to 15% limestone. There are still some specifications that limit or restrict or completely prohibit the use of Portland limestone cement. So that's something to be aware of. But the potential is a 5 to 10% reduction of CO2 depending on the level of limestone. And that change is something that can be done for most ready-mix producers and for most applications without any change at all. So it is currently widely available in Canada. As far as our production, Lafarge production, this is the only cement that we produce in Richmond, and it currently accounts for around 60% of the cement production at our actual facility. So those are the two main things that we focus on for cement, and then we start looking at how we produce lower carbon concrete. So these are things, options that can be implemented today. So most ready-mix producers would use some of these technologies. And the first one is the use of fly ash. So these are SCMs, or supplementary cementitious materials. So this is a byproduct of coal-fired power generation. Replacement levels are typically around max out at around 50%, but they can be up to 30%. Max of around 50%, but typically around 25 to 30% maximum. Again, not necessarily accepted in all specifications. You need to be aware of strength gain and finishability implications. And if you're looking at very, very high levels of SCM, you also need to be aware of what the curing requirements are for that concrete as well. Now, what's happening is coal-fired power generation is shutting down, so that means the availability of fresh fly ash is becoming more of a challenge as far as its availability goes. So that's something that we're dealing with as an industry. Over the last couple of years, fly ash availability has become much more constrained, so that's something to be aware of. And as far as the potential reduction of CO2, it's around between 10 and 20%, depending on how much you replace. But it has been around for a long time, but has limited future applicability because of those coal-fired power generations shutting down. But the industry is taking steps to address that by recovering wasted fly ash that had historically been put into landfills, for example, or detention ponds, and recovering that, treating it, and making sure that it's suitable for use in concrete, and then using that as a fly ash replacement. Slag is another one that some people may have heard of. So this is another name for this is ground granulated blast furnace slag, or slag cement. So this is a byproduct of iron production. So typically this would be something that occurs in the Hamilton, Ontario area. But the slag that's normally available in the sort of western parts of Canada and western parts of the US is actually coming in from Asia. So this has a maximum replacement level somewhere around 80%, but typically you would not use more than 50%, depending on your application. So it can be used at a higher level in comparison to fly ash. Again, can have strength gain and finishability implications and curing implications as well. Again, not necessarily accepted in all specifications. But because we can use more of this material in comparison to fly ash, the potential CO2 reductions are higher, again, depending on your replacement level, but between 20 and 30% CO2 reduction. It does have a long-term history of use, and at the moment, it doesn't look like there's the same constraints as far as the availability goes moving forward. There are other types of SCMs. Some of these you may have heard of. Some of them are commonly used in concrete, and some of them are just starting to be used. So one is ground glass, so taking recycled glass, grinding it up into a fine powder, and then using that in concrete. Silica fume is something that has been used for a long time, but typically only up to 10%. Natural pozzolans are available as well. So these are the sorts of materials that the ancient Romans would use to produce concrete. And then that recovered fly ash that I was mentioning before. Some of the limitations with these materials are how familiar the ready-mix producers may be in their use. They do tend to have regionally specific availability, so they may be available in one region and not another, for example. There may be limits to the use and specifications depending on the type of material, or they may not be accepted in specifications at all. As far as the potential CO2 reductions go, it is variable depending on which material it is that you're looking at. And in terms of status and viability, new materials are being identified all the time. So work with your ready-mix provider to understand what types of SCMs they have available, to understand how they can take action today in terms of reducing the CO2 associated with ready-mix concrete. We'll start looking at some emerging technologies now. So some of these I'll go into a little bit more detail, but there are basically 4 different areas where people are and researchers are working on some of these emerging technologies. These include things like alternative cement production processes. So that would include oxygen enrichment or hydrogen enrichment for the combustion, and indirect calcination. I'll get onto that in a little bit on the next slide here. There are alternative binder systems as well. So these are, again, similar to SCMs. These are materials that perform in similar ways to cement, but with lower embodied carbon. So some examples of those are silicium, geopolymers, LC3, and calcium sulfoaluminate as just some examples. Carbon capture utilization and storage is something that some people are saying is going to solve everyone's problems. And this is where you collect and capture the CO2 and either use it for other purposes or store it deep underground, like in a disused oil well, or a natural gas reservoir, or a saline reservoir deep underground. Some examples of these sorts of technologies: there's pond biofuels that have been operating for a number of years out in Ontario. Savante are a company that uses a solid absorbent for collecting the CO2. Dimensional Energy is a company that uses CO2 to produce a synthetic crude oil. And in Heidelberg Materials in Edmonton, they're actually setting up a CCS, a carbon capture and storage project, where they are capturing that CO2 and sending it off to storage underground. Finally, there's mineralization, and mineralization is converting CO2 into other materials. So some examples of those companies are Blue Planet, where they're creating a synthetic aggregate; Fast Carb, which absorbs CO2 into used concrete; Forterra, where they're creating a synthetic limestone; carbon upcycling technologies, they take SCMs and treat it with CO2 to improve the performance; CO2 concrete, which use CO2 to cure concrete; and Carbon Cure, which I'm sure many people have heard of, where they're injecting very small amounts of CO2 into ready-mix concrete. So depending on the type of technology that's used, you see very, very different CO2 footprints as a result of these different technologies. So I'm just going to look into some of those in a little bit more detail. So starting off with indirect calcination. So this is the lilac process. And what they're doing here is actually taking the limestone and using a heat source to calcine that limestone in a completely separate vessel. So because they're doing it in a completely separate vessel, they get a high purity CO2 stream versus some of the other technologies where they're capturing the CO2 from a stack, for example, from a cement plant stack or a coal-fired power generation stack. Those technologies are trying to get the CO2 purity up to 95 or above 95%. and maybe starting from as low as 10%, for example. In this process, they're actually achieving that 95% purity simply through the nature of the process itself. They are currently building version 2 of this system in Germany and looking to capture 100,000 tons of CO2 per year. The potential as far as its impact on the cement industry is up to 60% reduction, depending on what sort of heat is used to heat the lilac kiln or the lilac system. And this has ongoing pilot for commercial implementation, but it is actually looking fairly promising. LC3 is another one that I mentioned on the slide a couple of slides ago. So this stands for limestone calcined clay cement. So it builds on a synergy between the clinker, which is the traditional product for the production of cement, calcined clay, and limestone. So you can see the composition there. It is there are limitations in terms of the availability of the raw materials, so finding a suitable clay source. It's not necessarily accepted in codes and standards, so that's something to be aware of. But you can have a reduction of up to 40% depending on the specific ratios for the LC3 product and what sort of performance they get. There is ongoing commercialization worldwide. There's been a lot of activity on this over the last few years, but not very much activity in Canada or in the US at this point in time. CCUS, carbon capture utilization and storage. The image here shows a storage proposal. So one of the technologies the technology that is commonly used for CCUS is an amine-based CO2 capture, and the CO2 is sent to storage. So there are limitations with this. This is expensive to set up. The Heidelberg Materials project in Edmonton is estimated to currently be sitting somewhere between 1.4 and 1.6 billion as far as the capital investment for that. And it does double the footprint of the plant and significantly increases the power consumption. Now, they're actually installing a gas-fired power generation system to supply the power for this facility, and also capturing the CO2 from that power generation and putting it underground as well. There is degradation of the amine over time, so that does increase the operational costs, and you need to have a sequestration field for. And what I mean by sequestration field is where are you going to put the CO2? So in Alberta and the prairies, you're actually quite fortunate that you do have access to some of these sequestration fields. So they include things, as I said before, like used oil or exhausted oil wells, exhausted natural gas reservoirs. Those sorts of things can be used to store the CO2. Once it's underground, it actually turns into other geological materials. So it doesn't stay down underground as CO2. There is potential for up to 100% capture and reduction of the CO2 associated with cement production. And as far as the viability goes, there are several commercial implementations at various locations around the world, and the one that was probably the most advanced in North America would be the Edmonton one. At Lafarge, we're also looking at a CO2 capture and storage system for our actual facility, again, leveraging the access to those underground storage sequestration fields. I'm now going to switch gears a little bit and look at environmental product declarations. So everything that I've talked about so far is looking at how CO2 is reduced in cement and concrete. Environmental product declarations are how those reductions are actually measured and communicated to cement and ready-mix users or customers. So this is a diagram of various types of carbon. So the gray in this diagram represents the embodied carbon. The dark blue represents the upfront carbon as part of the embodied carbon. The sort of teal colored use stage. So there is embodied carbon associated with the use of structures and buildings. And then finally, the end of life embodied carbon. So those are the three sort of circles around the center. And then we have the operational carbon represented at the bottom. So for the most part, the EPDs that most manufacturers produce only cover these first three steps. Okay, so it only covers raw material supply, transportation of those raw materials to manufacturing, and the manufacturing process itself. So these are what we call cradle to gate EPDs. They're designed for business-to-business communication and only capture a portion of those upfront carbon impacts. One thing to bear in mind with EPDs is that it's more than just carbon. So although the carbon or the CO2 is presented on the EPD by this GWP or global warming potential number, there are a number of other environmental impacts that are also covered in EPDs, so much so that there are actually over 30 different indicators that you would be able to look up in a specific product, EPD. So just more alphabet soup compared to thinking back to that first slide where I was talking about some of the language that's used in this space. But now we're looking specifically at EPDs. So EPDs start with data. That data is what we call life cycle inventory data, or LCI. It can be industry average or generic information. It can be plant specific, and it can be product specific. The other thing that is needed for an EPD is what's called a product category rule. So this is the document that gives producers of products all of the rules that they need to follow to actually create an EPD, what sort of information is needed, how the calculations are done, all of those sorts of things. So that information feeds into an LCA, or a life cycle assessment. And that life cycle assessment takes two types of data. So it takes primary data. So this is the information specific to the production. So that would include things like electricity use, the actual production of a particular facility over a full year, those sorts of things, the fuel use, energy use, all of those things. There's also background data, and the background data are things like your grid intensity. So when you're producing electricity and using electricity, that there's a certain amount of CO2 associated with that electricity. So that's the background data. Or if you're transporting materials, for example, the transportation distance and the type, the transportation distance is primary data. The type of transportation and the CO2 associated with that transportation is background data. So all of that gets fed into the LCA, and from that, out of the LCA, we produce an environmental product declaration. And that environmental product declaration, in turn, creates more LCI, lifecycle inventory data, for other downstream EPDs. So, for example, we have an EPD for cement, for example, that provides LCI information for the generation and production of a concrete EPD. So the PCR is already done, so typically you don't have to worry about that. In terms of collecting data, that's the part that takes time for production of an EPD. And then generating the LCA and production of the EPD itself, that's the part that costs money. Okay, so what does an EPD actually look like? So here's an example for the current CAC, the Cement Association of Canada, EPD for cement production in Canada, split out into 3 different regions. In this particular case, this is for general use Portland cement. This is the Manitoba EPD for ready-mix concrete. So in this case, we're looking at a 35 MPa with a water cementitious ratio of 0.4. So this is the equivalent of a C1 or an S1 exposure class of concrete. So you can see the global warming potential that is in that top line. And if you're using and need to use this EPD, does provide a baseline for the particular type of concrete as well. So if you're looking for some generic information about what GWP for concrete in Manitoba looks like, this is the column that you would actually use. So for 35 MPa, 0.4 water cementitious ratio, with air is 300 kilos of CO2 per cubic meter of concrete. Another example here, this is one for a concrete in the US. This is a much more simplified version of an EPD, so they can look very, very different. So bear that in mind when you're actually looking at EPDs as well. And this one is actually a product-specific EPD for a specific plant. So they can be as little as 2 to 3 pages or as much as over 50 pages if you're looking at an EPD document. They can be specific to one product, such as that last example that I showed there on the right-hand side, or it can cover as many as hundreds of products in a single EPD document. It can be, again, as I said, be specific to one product, or it can be an average of many products, like the cement and concrete ones that I showed there for Canada and for Manitoba. They would be an average of many different products across the province of Manitoba, for example. One thing to bear in mind is that they are only valid for 5 years, a maximum of 5 years, or a major change in the production. There are some tools for EPDs for those people that are interested in how EPDs are produced or need to find out about how to get their own EPDs. So if there are ready-mix concrete producers here on the call, these are some of the tools that you could use. So WAP Sustainability, they have this tool called Theta EPD. They do have functionality to produce EPDs for a variety of different materials, including cement and concrete. The GCCA, which is the Global Cement and Concrete Association, they also have a calculation tool that provides the ability to produce EPDs for cement, concrete, aggregates, and precast. And then EC3, which is not a tool to actually create EPDs, but it is a tool to collect and manage EPDs. So if for those people in the on the call here that are interested in where to find EPDs, this is one place to actually go looking for them. So it's put together by Building Transparency. EC3 itself stands for Embodied Carbon and Construction Calculator. It can be used to directly compare EPDs, and through the creation of this database, it has driven the transition to electronic EPD. So moving away from PDFs and things like that to electronic documents that can be communicated directly between on a computer system. One other thing that some people may have heard of or may not have heard of is Carbon Star. This only calculates CO2 for concrete. It does include sequestered CO2. So if you have a system where you're using carbon cure, for example, or you're getting cement from once the Edmonton plant gets up and running with their sequestration, if you're using that cement, you could actually use this calculation rather than EPDs to calculate what your carbon impact is for the specific ready-mix concrete that you have. It is intended to be a quick, easy, and simplified calculation in comparison to an LCA. The document itself was put together as a technical specification between CSA and ASTM. It is available free. There are no tools to calculate this, so you would have to come up with your own tool. And what's actually happening at the moment is CSA is converting this from a technical specification into a full-blown CSA standard. So where does all this fit into what we call whole building or whole structure LCAs? So the dark blue box that you see here, that is the whole life carbon. So it includes all of your embodied carbon and your operational carbon. The green box represents your embodied carbon. So it's all of these other pieces. So your upfront carbon, your use stage embodied carbon, and end of life carbon, but does not include your operational carbon. So that's sort of where all of these different parts of the LCA structure fit within doing a whole building LCA. There are some things to bear in mind is that operational water use is out of the scope of whole building LCAs. And supplementary, there is a module D, which is information beyond the building, beyond the scope of the LCA and beyond the lifespan of the building itself. There are tools for a whole building LCA as well. So there's Athena, have an impact estimator for building. It is a free tool, but bear in mind that it's only a partial analysis rather than looking at all of those different parts of the LCA. They're looking at a limited subset of that. One-click LCA, they have free and fee-based systems. This is a tool that was specifically designed for the construction industry. So many of the people and LCA practitioners and architects and engineers are actually using this tool because it was designed for the construction industry. So it's set up that way. Some of these other ones, like SEMA Pro, Gabi, and OpenLCA, these are tools that you could conduct an LCA, but they aren't really specific to the construction industry. So they take quite a bit to learn how to use them. EC3 I touched on before is free, but only covers A1 to A3 modules. And then finally, Tally and TallyCat. These are fee-based systems. TallyCat is actually Tally was taken over by Building Transparency, so the same company that produced EC3. And they've been working on the production of TallyCat, which is a tool that links directly into EC3, and it's a Revit tool for those familiar with that terminology. Okay, so how is all of this tied together? So there are LEED and buy green policies. So there are credits available in LEED for doing LCAs and providing EPDs. And there are buy green policies, and the buy green policies are basically the public procurement policies intended to favor more sustainable materials. So there's one at the federal level, and there are municipalities that are active in developing and publishing policies as well. At the federal level, it's called the Standard on Low Embodied Carbon in Construction and includes concrete. You can see the link there. It applies to all federal government projects over 10 million. Where more than 100 cubic meters of concrete is used. So that, generally speaking, means most federal projects. And what they actually require with this standard is to actually have a GWP reduction of at least 10% in comparison to the baseline. And that baseline would be what is shown in the provincial EPDs. It does require product-specific EPDs, and there are exemptions for high strength or early high strength or high performance, as well as cold weather concreting and things like that. So finally, I just want to touch on prescriptive, touch on some pieces around specifications, and specifically looking at prescriptive versus performance specifications. So prescriptive specifications, they tend to have these sorts of elements. They tend to have strength and information there, defined what is to cementitious materials ratio. There can often be limits on cement, or either in the type of cement or the amount of cement that can be used, limits on the type and amount of SCMs, limits on admixtures and additives. But when you're looking at prescriptive specifications, the primary risk associated with the specifications and the performance is with the owner and the designer. So these tend to build on the history of construction and empirical relationships, but they don't really allow for a lot of creativity and innovation. Some examples of prescriptive specifications. Here's one on the left. So you can see here it's not uncommon to see strength. In this case, they have a maximum coarse aggregate size. They have air content listed here. They have slump and a maximum water to cementitious materials ratio. On the right-hand side here, we've got an example of some specification language. So if somebody wanted to use GUL cement, the submission needs to include a signed and sealed letter prepared by a materials specialty engineer. So for projects that don't have access to a specialty engineer, that can really limit and restrict the use of GUL cement. Here's another example, which is a very restrictive and prescriptive specification. So again, you've got the compressive strength, the maximum water to cementitious materials ratio, but they also provide a minimum cement content, maximum pozzolanic material content. So that would be your fly ash and slag. They give the nominal coarse aggregate size, but they even go down and say how much sand needs to be in a particular mix as well. So these are very prescriptive. That's an example of a very prescriptive specification. Conversely, if we look at performance specifications, these tend to be a lot more flexible. They provide, they really look at the functional requirements for the specific element and structure. They provide both plastic and hardened properties and requirements. They may include other measurable requirements, such as maximum CO2 associated with the concrete. And in this case, the primary risk is with the producer and the contractor. But the advantage with these types of specifications is that it offers the suppliers and the contractors the flexibility to achieve what the project goals are. Now, difficult to find some really good examples of performance specifications. So I've only got one example here, but you can see here they look at the different building elements, only provide the compressive strength that's required and the exposure class. So that's the only information that is provided as part of the specification. So it's up to the ready mix producer to fill in the gaps and work with not only the owner and the engineer, but also with the in particular the placement contractor and the general contractor to make sure that the concrete that they're providing not only meets the requirements of the specification, but also is able to be placed properly with the equipment that is intended to be used. And with that, I'll open it up to questions and any discussions that you may have. And thanks for your time.
Oh, well, thank you so much there, Matt. So if anybody has any questions, you can raise your hand and we can ask you the questions. While we're waiting for that to happen, is there anything else that you would like to say about, has there been any research about incorporating waste plastics and embedding polymers into concrete?
Yeah, there has been some research around incorporating plastics. One of the issues with incorporating plastics is and some of the other materials that have been researched in terms of looking at what can be put into concrete is that plastics float, which does cause some issues as far as finishability of the concrete and can cause some issues in terms of the visual aspect of the concrete as well. So those are some of the limitations as far as using waste plastics. But as sand is becoming more and more of a challenge as far as its availability, some producers and some researchers are looking at very small plastics rather than sand to form that fine aggregate in the concrete matrix.
Okay, thank you. So just a reminder, folks, you can drop your questions in the chat or raise your hand. Our next one is just looking at the table 3 EPD slide. There is a row talking about abiotic impacts. Are there any metrics your industry looks at regarding biodiversity loss, especially in the excavation stage?
So those would be considered land use changes, and some of the emerging metrics that are covered in EPDs, there's not a ton of very good research around them. So they're often listed as emerging indicators, and most EPDs would actually have a little disclaimer around a lot of those indicators to say that they are emerging indicators and the information presented may not be reliable. Now, that said, speaking for Lafarge, yes, we do have biodiversity targets and initiatives within our company. I haven't looked specifically at other producers in Canada, but I would think that many of them do. But they may not be covered and really highlighted very well in a product like an EPD.
Okay, thank you. Okay, so can you talk about Lafarge's eco-packed concrete and how you are getting the CO2 reductions that you are claiming?
Okay, so I'm actually going to put up this EPD. So our EcoPack concrete is really leveraging a lot of our experience that we've gained over a number of, well, over decades, really, and using our technical experience and expertise in terms of how, with a focus on CO2. So when we are designing concrete historically, we haven't necessarily focused at and looked at CO2 specifically as far as the CO2 footprint of the concrete. What we are doing with EcoPact is having a very, including that as part of our decision matrix as far as how we put concrete mix designs together. So that takes us down a certain avenue as far as the decisions that we make as far as designing different types of concrete. So there are things that we do like higher levels of SCM. So showing this table, if you look at the header of the table, you can see we have different levels of SCM. So for example, this column here, the GU column, is without any SCM at all. Then we have 10% fly ash, 20% fly ash, 30% fly ash, 40% fly ash. Then we switch over to a column with GUL and GUL 10%, and I cut off that part of the table header, but I think that is a 20% fly ash with GUL. So you can see as your SCM content increases, your GWP drops. So this is one of the levers that we use for production of EcoPack concrete, as well as optimizing a few other factors on the concrete mix design. So as far as EcoPacked concrete itself goes, we as a company, we require at least a 30% reduction in GWP in comparison to a baseline to qualify for EcoPacked. And then we have high levels of reduction to qualify for what we call EcoPack Prime and then EcoPack Max. And those are 50% and 70% reductions. The important thing to bear in mind with EcoPact, and the same with these different technologies that are available in different regions, you do have to work with your local suppliers to understand what is available in your area and what the options may be. So although you may want to use EcoPack Max, for example, that may not necessarily be available for the specific geography that you're looking at for your project.
Okay, thank you. Morwena, do you want to unmute yourself and ask your question?
Sure. Hello. I'm lower my hand. I'm coming from the world of real estate, so I'm not going to lie. A lot of what you said went over my head for the smarter folks here. I'm more curious about how the road looks moving forward. Maybe this is more of a question for Sustainable Building Manitoba, how this could become more mainstream, some of these technologies, like when Manitoba Building Code or something like that, which I understand they just lowered our building the codes. Anyway, so that's sort of my question, is what the road looks like moving forward, and how we can make these sorts of technologies more mainstream and available to the public for basic things like home building.
So the things that are available mainstream today aren't going to change appreciably for the next little bit, at least. So that includes things like SCMs, the use of fly ash and slag, for example, that I highlighted earlier. As far as what's coming, those emerging technologies, some of them are going to be available sooner rather than later. So, for example, the Edmonton, the Heidelberg Edmonton carbon capture system, I think they are saying that will be operational by 2025 or 2026, that sort of time frame. Some of the other technologies that I talked about, like lilac, and the technologies that I didn't really go into in much detail, some of those are barely out of research. Some are so looking for commercial viability. Some of them are beyond research, and some of them have had attempts at commercialization in the past and failed. So sometimes some of that may just be a case of bad timing and being, having the right solution, but just presenting it at the wrong time. So there are things that are changing. It's a tricky question to say exactly what's going to be happening when, but certainly I would say keep an eye on and keep in contact with your ready-mix suppliers to understand what options they have available in the specific area and what they are looking at in the future as well.
Yeah, thanks. And just to add to that, people's awareness of the options is a huge piece of adoption as well. So that's one of the reasons we do sessions like this. And then, as well as you mentioned, the building codes and different regulations that limit how much you can emit is also a big piece of that adoption curve. So
yeah, and another piece of that is that that the federal carbon standard as well. So once the feds start introducing requirements around CO2, that's when many producers, if they're bidding on federal work, they will be required to meet that standard. So that really drives a lot of innovation in the industry as well.
Yeah, exactly. So until then, it's up to the person who's paying for the project to want to do that, take those actions. So again, that education piece is super important. So the next question is coming in from Archie. In the savings shown in traditional SCM, do the savings include the production of the SCM?
Yes, they do. Yeah. So what's shown on a document like an EPD, in terms of the production of the SCM, it depends on the SCM itself. So for the most part, SCMs like fly ash and slag, for example, and silica fume as well, these are byproducts or traditionally waste products of that industry. So fly ash as a waste product of coal-fired power generation, for example, or slag being a waste product of iron production. How the accounting is done in North America at the moment is that these materials are considered byproducts and not co-products. Because they're considered byproducts, the CO2 associated with their initial production is associated with the product that they were producing. So for fly ash, for example, the CO2 associated with burning coal to produce fly ash, that CO2 is associated with power production and not with the fly ash. It is approached differently in Europe, where they can be considered co-products. In that case, they actually take a portion of of the CO2 associated with its initial production and assign it to the different products that are actually made. Does that make sense? But in all cases, the transportation of getting that material from where it's generated to where it's used is included. And if the product needs to be treated, or something needs to happen to that product for it to be used, that is also included.
Thank you. All right, Leslie, I see your hand up. Do you want to unmute yourself and ask your question?
Sorry about that. Hi. So I'm similar. I try to absorb everything you were saying, and some of it went over my head. I'm coming from an angle where I'm working to just help with the transition to clean energy, but doing it. What I'm curious about with your industry, what are they forecasting, or what is the future looking like as far as opportunities for closed loop recycling? Is that something that's in the cards for down the road as part of the system?
By closed loop recycling, are you talking about extended producer responsibility type?
So, for example, we get a large property and it's being demolished, and it was predominantly built using cement. Is there an opportunity to take that original product and then recycle it into a future product? Is that something on the horizon?
Right. Yes, there are those opportunities. As I said in one of the slides in the deck here, concrete contains recycled materials such as fly ash and slag, for example, and it is recyclable itself. So yes, you can take that concrete, crush it, and then use that crushed concrete to produce new concrete or fresh concrete. There are some limitations around that, and currently CSA being the standard that we actually have to produce concrete to, it allows the use of recycled concrete aggregate to a certain extent, but there's not a lot of information in there. But we're expecting the next version of CSA to provide more information about what sorts of concrete can be used to be recycled to create fresh concrete, as well as the restrictions and limitations and things like that, just to ensure that the concrete that's being produced is safe and meets the requirements.
So given what you said, you do see that forecasting as a potential opportunity in the future then?
Yeah, I mean, yeah, there's recycled concrete that is used today. Some people are using it to produce fresh concrete. More typically, the recycled concrete gets received, gets crushed. The steel will go out for recycling, and then the crushed concrete can be used for road base, for example. So where you would traditionally use virgin aggregates, you can use recycled crushed concrete. And it actually, as far as a road base goes, it actually does produce a very good road base, because there's always a little bit of cementitious properties left in concrete, even after decades of use. So when that crushed concrete gets wet, that can trigger that hydration reaction, and that can actually start turning hard as well. So you get some added benefits by using recycled concrete for things like a road base.
Exciting.
Just a follow-up question to that: is there a plant nearby that does that work?
We do have a plant in Manitoba that does that sort of thing, but we don't currently use the concrete in fresh concrete at the moment.
Whoops, sorry, muted myself. So we are at 1 o'clock, but we've got one final question. So Matt said he was up for sticking around for it. So is low carbon concrete price competitive with conventional concrete? And can low carbon concrete be used for all types of structures?
So the first question, again, work with your local ready mix supplier to understand what options they have available to them. But generally speaking, yes, low carbon concrete is competitive with conventional concrete. There may be a slight premium, depending on how big the reduction is that you're looking for as far as your project goes. So bear that in mind. And then in terms of low carbon concrete being used for all types of structures, typically yes. As I said, when you're getting into much higher levels of SCM replacement, you may need to look at potential schedule implications, but there are ways to deal with that, as well as the curing of the concrete as well, just to ensure that it is actually cured correctly to maximize the strength performance.